It's an honor for me to introduce you to John Barron. This last year he has been instrumental in what we call NeRF, so neural radiance field, and he's going to talk about that domain. Thank you.
Thanks so much for the invitation. Thank you for the introduction. It's wonderful to be here. My name is John. A little bit about me. I feel like I'm kind of here as like an ambassador from AI land, but we're not so different, you and I. I came up at UC Berkeley doing inverse rendering stuff, trying to, basically I took the computer vision class, I took the graphics class, and I was annoyed that the graphics class wasn't the transpose of the vision class, and I've been trying to reconcile those two things ever since, trying to make a differential rendering engine so you can tease apart the 3D world that made an image. And these days we're still doing that same thing, and now it's under this umbrella of NeRF, and now it really works. It works really well. And that's kind of like my high-level, like I guess, academic interests. But at Google, I've spent a lot of time working on kind of subsets of this inverse rendering problem of disentangling the things that made an image into its constituent components and then mixing them together. Or at least that's how I think of them. And probably the most visible one is Google's low-light photography modes like HDR Plus and Night Sight. These are on the Pixel phones and widely used there. I contributed various things to that. I also was heavily involved in the kind of the advent of portrait mode. I built the first few iterations of Google's portrait mode, the depth estimation and the blurring stuff. Things like portrait lighting, various other photographic effects. And I've also worked on multiple hardware camera projects that have received varied amounts of success. I'm very happy to talk about any of this later this evening over drinks. So just zooming out. So I'm going to be talking about some inverse rendering, some graphic stuff. I just want to kind of lay some groundwork of computer graphics. What's graphics? What's going on here? So there's this very high level kind of paradigm split in computer graphics between two families of algorithms. The first is rasterization. This is what most graphics today, anything on a GPU, well, I guess not anything on a GPU. Most video game engines are doing this sort of thing. You have a for loop over objects in the scene, for loop over triangles, say, in a triangle mesh, and you slam them onto an image plane, and then when you're done, you have an image. And there's a separate paradigm, which is ray tracing, and here you have a for loop over pixels in your image, and for each pixel, you render it by casting a ray out from the center of projection of the camera out into the world, and you see what it hits, and then maybe you bounce off of that, you look at the light. And we're going to be building a ray tracer today. There's also another kind of paradigm split in graphics. This is between mesh rendering. So mesh rendering is kind of the normal mode of rendering where the world is made of a bunch of hard and sharp little triangles or quads or what have you. And they're probably fully opaque or they don't exist at all, and you render them and you get an image. And there's a different paradigm, volume rendering, where the world is not made of hard and sharp things, but it's made of soft, fuzzy, mushy stuff, probably a voxel grid. You take space and you chunk it up into a grid, and things are partially occupied or fully occupied in that grid, and then you can express semi-transparent things. This is widely used in medical imaging because we have scanners that kind of produce these things natively. And volume rendering has been a thing people have been very excited about for a long time. And there was a sense, as a quote in the 80s in the graphics community due to Jim Kajia, that says all rendering will eventually be volume rendering. People have expected this to kind of eat rendering, and it hasn't really happened yet. But we're kind of doing that. We're going to be trying to do that today. So we're going to be building a volume rendering engine. And that kind of, those two things together bring you to NeRF. So NeRF, it's an acronym. The neural is there because it has to be. I'm obligated to have neural networks in everything I do. It's a joke. There's a neural network at the core of this. And what the neural network is parameterizing is radiance, so the amount of outgoing light of a point in space. And there's a field of that, and the field here just is in the calculus sense of field. So there's a continuous function that you can kind of probe wherever you like. This started in this view synthesis literature. So the thing we wanted to do was take a bunch of images from a camera of some scene, some 3D scene, maybe like 100 images, feed it to some model, and then get new images of that thing from that model. And the way we end up doing that is basically by doing 3D reconstruction with this NeRF in the loop. And it works very well for view synthesis, but over time, NeRF has kind of evolved into a more general purpose primitive in larger pipelines for basically differentiable volume rendering, differentiable rendering. So if you need to be able to optimize over a 3D thing where gradients are flowing into it, a NeRF is, or a radiance field is the way to do it. So at its core, a NeRF is super simple. This is going to be the only slide that has a neural network in it, so don't worry. So there's this little neural network, and for our purposes, just forget that it's even a neural network. It's just a function approximator. It's a thing that maps inputs to outputs whose parameters you can update with gradient descent. And it maps 3 numbers, x, y, z, a point in space, some 3D location, to 4 numbers as output, and those are RGB, color, and volumetric density, that is from 0 to infinity, where 0 means this is empty, there's nothing here, and infinity means it's a hard wall, it's fully opaque. So you take that neural network, and let's imagine first that we've already trained a NeRF. Someone has given us the weights of that neural network, and we just want to render an image. The way you render an image is you do a for loop over all your pixels in your image, and for each pixel, you cast a ray from the center of projection of your camera out through that pixel, and it goes out into the world, and then there's nothing for it to intersect, right? This isn't like normal graphics ray tracing where there's spheres and toruses. So what you have to do is you have to extract a bunch of XYZ coordinates along that ray. Those are those black dots shown there. And you feed each of those XYZ values through this neural network, through this learned function approximator. And what it produces as output is a series of colors and densities. And then you just apply kind of basic volume rendering to that output. And you march from the back of the ray up to the front doing alpha compositing. So if something is fully opaque, it completely clobbers whatever values were behind it. That's just, all I'm saying is if there's a hard wall, you can't see through it. And if it's 0, if the density is 0, then you ignore that color and you just continue showing the thing behind that. So you march from the back of the ray up to the front, and when you're done with this process, you have an RGB value for that pixel, you put it in the pixel, and then you move on. You have now rendered that pixel, and you're good to go. And the training procedure is just doing that a bunch of times, where someone has given you a bunch of images. So I'm gonna give you 10 or 100 images. We're gonna assume that the camera poses are known, so we know where in 3D space the camera for those images lies. In practice, you solve for that using structure for motion, using established tools and computer vision. And then you just randomly initialize the weights of your neural network to be small and random, as is common practice. And then you just render an image, and the rendering you get out at first is garbage, right? It's completely meaningless. It's just a pea soup fog kind of thing. But you can compare it to the input image you received. You can compute the error, and you can get the gradient of that error, and you backpropagate it through the rendering engine onto the weights of your neural network. And you do that about 10,000 times, and the surprising thing is that the thing you end up with is a 3D model. And it ends up being a very accurate 3D model. There's no real reason why this has to happen. You could, in theory, reconstruct a bunch of kind of postage stamped sized little 2D images floating in front of each camera. But in practice, that's much harder than actually just doing 3D reconstruction. So the secret here, the reason why this works, is that if you sit down and you write down a volume rendering equation, like in this case it's Max 1995, that citation should be there, you end up with a bunch of neural network ops, which is perhaps surprising. You end up with a bunch of things that are just very straightforward to implement in JAX or PyTorch or TensorFlow. You can implement this whole thing. All of NeRF, the first paper, was implementable in about 200 lines of code. It was a cool cosmic thing, just that like volume rendering and deep learning just have this nice synergy. And the way to think about that is you need gradients to kind of flow through your 3D model. And the only way to do that is to have it be kind of blurry and fuzzy. If you have a bunch of hard, sharp triangles, gradients are either 1 or 0 and they all die and things don't solve. So here are some results from the first NeRF paper. These are just some scenes of the UC Berkeley campus where we walked around and took a few images that are all kind of facing forward, and we reconstructed NeRF for the scene and we moved the camera around. And you can see it looks quite good. These results are 4 years old now, but they hold up well. There's a lot of thin structures, a lot of shiny things. That pond is reflecting. That's actually a fake reflection. There's a mirror of the world underneath it. And this really made waves when it went online because people were not used to seeing these results from 3D reconstruction algorithms. Usually you expect to see something that looks like it came from a computer vision algorithm, and these basically look like photos. And like I said, all we're doing here is 3D reconstruction. This is just 3D reconstruction where a complicated and confusing neural network has encoded the geometry of the scene into itself in a way that's kind of counterintuitive, but it is a real 3D model, and you can do 3D model stuff to it, right? So here on the left, we're rendering an image, and on the right, I'm rendering a depth map. And the way you do that is whenever you cast a ray, you just measure how long it takes for that ray to stop traveling. In practice, you measure the median termination depth into this volumetric fog. You can think of it like you're shooting a bow and arrow at a target, and it sinks in and then stops. So you take that, you get a depth map, and these are like unusually good depth maps. They have lots of thin structure, clean edges, none of the sort of edge fattening you're used to seeing in stereo and things like that. And roboticists got when this paper first went online, a roboticist emailed me saying like, do you realize how good these depth maps are? And I was like, yeah, they're good. So this has been another kind of life that NeRF has taken on in this depth sensing world. And we've been doing this for a while, for about 4 years, and there's a lot of papers out there, a lot of progress. This is kind of the latest and greatest from my team. This was at ICCB this past summer. This is a NeRF. This is a rendering of a NeRF of my house, because we needed a house that no one had any IP complaints about, except perhaps my wife. And you can see it's working really well. Before we could just move the camera a little bit, now we can just fly it through the first floor of a house. It's not quite photorealistic, but it's damn convincing. Yeah, so when we put this paper online, this video kind of went viral and on Twitter and Reddit and stuff. And it was at the top of the Be Amazed subreddit, which is where people just post mind-blowing stuff. And the title of the post was, "An AI generated this house," which is like kind of true. I mean, really, this is just 3D reconstruction of a house. But obviously, for the Reddit audience, that's like a bit of a nuanced sort of distinction. So my wife and I spent a few hours just scrolling through Reddit comments, things like, "You can tell this house is AI generated because it has way too many chairs." We just have a lot of chairs. I don't know, young kids, you need a lot of chairs. I don't know. So yeah, so you can try this stuff. This is shipped to Google Maps. This is Sundar Pichai, the CEO of Google, presenting this stuff a couple of years ago at Google I/O. We've NeRFed the insides of a bunch of restaurants using the same technology that I use to NeRF my house. And you can try this on your phone right now if you want. You can kind of scrub through interactively, which is nice. It's basically showing you a pre-baked 360 video that you can kind of move through. So it's not full 6-off, but we can do that too. So I'm gonna quickly go over kind of some greatest hits of progress that's been made in this space. So one problem with NeRFs is that they're slow, but we're aware of that, and there's a lot of work on trying to speed these things up. This is a paper that was at SIGGRAPH this past summer, where we basically just take this NeRF, which again is a kind of 3D model. It's just one that's slow to render and it's kind of complicated. And we can export it, we can bake it out into a kind of video game engine friendly 3D representation that you can render in real time on a browser. You can run this on your phone if you like, if you follow that link there. And this is a real 3D mesh, so you can just do whatever you want with it. You can put it into other environments, you can retexture it, you can relight it. There's anything you would want to do with a 3D model, you can basically do with these things. Another problem that's near and dear to my heart is this problem of scale, which closely relates to the problems of aliasing and anti-aliasing. NeRF basically assumes that every object exists at a single scale, and that's a problem if you want to be able to pull away from something or get up close to it. So there's a neat line of work where you can basically endow these models with a sense of scale, which means that when you zoom in, you get nice edges. When you zoom out, you don't get jaggies, which is what you see on the left there. Lighting is another big problem. Because in general, if you take a bunch of images of, say, the Trevi Fountain, some tourist destination, they were probably taken by different people at different times. So the lighting is inconsistent across different scenes. But we can basically take images like that and recover. What you're seeing here is not just a NeRF, so much as it is kind of a parameterized family of NeRFs, where the appearance of the object is this latent space that you can navigate through, and that lets you change the light, not only discount lighting variation of input images, but change them when you render it. So we can do things like not just move the camera, but also change where the sun is and the time of day. Motion is another big thing. First NeRF paper, everything was static. You can just extend the model a little bit and then have a field of not just radiance, but also of deformation. And then you can deal with scenes with video sequences of things that are moving around, like you see here with this 3D printer. And because there's no mesh here, this is just a weird volumetric thing, you can recover things that are hard to express with a mesh, like you got espresso here being poured into a glass. So the espresso and the glass are both hard to model as meshes, but you can model them straightforwardly as radiance. So now, this is a part that I thought would be fun to deep dive into for this audience. So this is a paper we had at CVPR about a year and a half ago. And the focus here was on, I mean, ostensibly it's about low light imaging, but the way I think of this paper is that it's primarily about kind of reconciling NeRF with camera design. Of like what is the relationship supposed to be there? So, so here's NeRF, a really cartoon view of NeRF. We take in some JPEG images and we shoot rays through the center of each pixel. And this is really all we're going to do in this paper. We're just going to assume that we have raw sensor readings instead of just someone else's JPEGs. And this is a small change philosophically, but it has like surprisingly deep ramifications in terms of what you can do with this technology. So the original NeRF paper, what do? We walked around with a DSLR and we took a bunch of images and we let the camera turn those into like nice sRGB JPEGs. And then we took those JPEGs and we fed them to NeRF and we recovered a model. This works fine, right? If your JPEGs are fine and if the auto white balance and auto exposure of your camera are somewhat fixed, even if they're not fixed, this can work basically fine. It starts to be a problem if you have things like noise, but it works. And so if you think about what's happening here, the NeRF, the 3D model we've recovered, kind of exists in sRGB space. That's the kind of like world it thinks the world that we're living in. But that's not really the world we live in. And so this project was about kind of redrawing the box around what is within domain for the NeRF. So instead of taking an image and allowing our camera to do all the conversion, demosaicing, denoising, white balance, auto exposure, et cetera, tone mapping, we said, okay, no, here's raw sensor data, just a raw Bayer image of photometrically linear light intensity readings that we've gotten. And we're going to train a NeRF in that space. And this ends up being pretty simple, right? You kind of just grab different data and you have to change the noise model, and there's details I can go into, but I'm just going to skip right past that. The thing this really gets you is a NeRF that now exists in photometrically linear space. So this NeRF is in world units. It's not in camera units anymore. Why does that matter? Well, for one, in world units you can reason about noise a lot more easily. I'll go into that. But the more exciting thing is that now your camera is just entirely defined with software. So I can take this photometrically linear raw NeRF of the scene, I can move the camera, I can render a new image that looks like a raw image. It doesn't look, it's perfectly demosaicked because I can just ask for all RGB values for every pixel instead of asking for Bayer quads. And then I can just do whatever my camera would do in software. I can re-expose it, I can change the white balance, I can change the tone mapping, I can do a bunch of tricks in this photometric linear space that I wouldn't be able to do otherwise. So here's what that looks like. So this is an image from a scene that we took. As you can tell, it's a nice little dinner lit by candlelight. Someone's eating a book, I guess. And there's a zoomed in area there that you probably can't make out the contents of. And you guys know how noisy images look. If someone gave you a noisy image, I mean, the thing you would probably do is to try to denoise them. This is kind of the state of the art from CVPR land of single image denoising for the scene. And it kind of works, it's doing something. You can kind of see the beginnings of an object there. And here's what our model does. So you can't see this here, but there's several other images of the scene. So we've got maybe 100 images of the scene. And all we're doing here is we're going to recover a NeRF of that scene from all those images and render a new image from the camera that is located at the input image's orientation. And you can see it works well. You've denoised the image. You can see the little bulldozer there that we use for all of our experiments. And just is a really severe amount of noise that we're able to reduce or able to eliminate. Without actually doing denoising, we're just doing 3D reconstruction, right? But it works well. And this isn't just an image, right? This is a full 3D model that we have kind of denoised out of a bunch of noisy observations. So we can do anything you'd want to do with a 3D model with it. We can change the viewpoint. It holds up well, it looks good. But beyond that, we can just start messing with our camera, right? We can change the exposure. So here we're just bracketing in software these renderings of this photometrically linear 3D model. And you can see the candle gets big and the candle light gets small as you change the exposure there. We can change the tone map, which yeah, this is the sort of crowd that would care about changing the tone. Yeah, but it's hard to convey how exciting that is, but I think it's really cool. And one thing that I really like is we can do things like change the focus, right? So we have a full 3D model that we are ray tracing, and you can do a lot of things in that setting, right? You can just change your ray tracer to have a thick lens instead of a pinhole, and then ta-da, you have portrait mode, you have background defocus. In practice, what we're doing is just rendering off an image with a bunch of Z slices and then blurring them with a disk blur, but it's qualitatively the same. And this is really hard to do if you don't have photometrically linear inputs, right? Because you don't get those highlights popping into nice bokeh balls. And this is the sort of problem you really, really need to solve in a photometrically linear space. So here are some more results. So these are, Ben Mildenhall, the first author of this paper, just went out to London where he was living at the time and just took a bunch of great shots of London at night. And you can see, yeah, it's a nice scene that we've recovered, 3D model. It looks good. This is what would happen if you ignored this paper and said, I don't care about this stuff. I'm going to just denoise all of my images using the latest and greatest denoiser, and then feed them to the last NeRF paper. And this works very poorly, right? Because every time you denoise one of your images, and first of all, you're going to get it a little bit wrong, but also you're going to be inconsistent from all the other images you've taken of that thing. And then you have a bunch of inconsistent 2D images that you then try to reconcile into one 3D model. They don't agree, you end up with a bunch of weird stuff. In contrast, this result had no denoising algorithm at all, right? It's just NeRF where we changed the loss function basically to obey the noise profile of our image. Here's some more wonderful results. We're in a church. There's exposed lighting, or overexposed stained glass windows that if you blur them out, they become these nice balls, and the candles in the foreground are doing what you'd expect. Here is another candlelit scene of our favorite rendering textbook. Everything's looking the way you'd expect. This result is one of my favorites. So we're going to focus behind the Lego truck there for a little bit. And you can see when we do that, the Lego truck disappears. This is not surprising. That's how an actual camera would work. If you focus on something behind something with thin structures, those thin structures would get blurred away and you basically see through them. But this was like as someone who worked on portrait mode for many years, this is the white whale of background defocus in a kind of non-NeRF context, because it's very hard to take one image in a depth map and then re-render it so that you can see through the stuff that you've occluded in that one image. But in this case, we're just, it's just a ray tracer basically, like the optics all work out fine. More thin structures and overexposed things. This is a good one. Sorry for the religious overtones. Here is a piano, Ben Mildenhall's piano. This one I really like because you can see when the camera focuses in the background, so the camera's going to focus at a far depth, you can see there's a bookshelf reflected in the piano there. That is in fact a bookshelf that's behind the photographer when they took the picture. So it's not real, what is real in this context? What is actually happening is a mirrored copy of the bookshelf was reconstructed behind the piano, and that little front panel of the piano was made semi-transparent so that you could kind of see the bookshelf. And when it goes out of focus, you can see the bookshelf blurs out, but the piano doesn't. This is, I think, pretty magical. This is a really hard thing to accomplish with like an image and a depth map. You really need a full 3D model for this to work. So what if you don't care about 3D? That's fine. That's cool. Totally understand. Even if you don't care about 3D, even if you don't really want to do 3D reconstruction, the results in this paper suggest that this is still actually the best way to do just denoising. So if someone gives you a burst of images of, in this case, a static scene, and a lot of images, to be clear, the best denoising performance we got on this benchmark we made was from just running NeRF with a different noise profile, from running this raw NeRF model. This outperformed a bunch of big neural networks that were trained just to denoise. And we don't really have any learning really involved. Like it's just optimization at test time from a bunch of input images. And I think this is pretty striking, right? Like this is a kind of surprising result. But basically, the inherent difficulty of multi-image denoising is reconciling what patch corresponds to what other patch in another image. And what we've done instead of trying to solve that problem is we just reconstructed a 3D model And in the process of doing that, we perfectly resolved the correspondence problem. And the pixel, the color value of a point in space is just whatever the average is subject to the noise model after those correspondences have been found. So obviously I'm very excited about this stuff, but I want to be very frank about its limitations because it has many. So this model that I've detailed is very slow. It's slow to train, it's slow to render. That zip NeRF of my house that I showed earlier takes about an hour on 8 GPUs to recover, and it takes maybe a second or two to render a frame. You can solve some of these problems. We're getting better at this all the time. These NeRF models get 10x faster every year, but this is still, a far cry from being something you could run on a phone. This paper assumed a static scene. You could relax that to support dynamic stuff, but we haven't done that in this line of work, and I imagine you'd take a quality hit if you did that. We assume a known set of camera poses. In practice, we solve for that using a structure for motion package, call map, which is like a state-of-the-art, 2016's version of state-of-the-art stereo. It is a little surprising this worked at all because the images are so noisy, and posing cameras for really in very high noise regimes is kind of hard. So this problem is solvable, but it does make it less applicable and kind of slow. But there's huge advantages to this line of work, to this sort of approach. So we can do a ton of stuff, right? We can do denoising, multi-image denoising, and apparently that's the best way to do multi-image denoising in terms of PSNR. We can do view synthesis because we have a 3D model and we can just render off new views wherever we want. We can put the camera anywhere. We can change the exposure, we can change the defocus, we can make the foreground or the background blurry, which is hard to do. And we have depth maps. We have really beautiful depth maps with everything. So any sort of image effect you might want to do with depth compositing, we can do that, no problem. And these models are really simple to build on. Again, going from just JPEGs to raw data was really just a few lines of change. The hard part was building the data loader, right, or loading in the raw images. But the training loop is literally just a one-line change in terms of what the loss function is. And we open source all of our code. You can build in these things quite easily. And one thing that I think is really exciting, possibly most exciting for this audience, is that this whole thing is totally agnostic to camera design, right? So we had Bayer quads, so we had a little loss function. The loss function needed to know that the red channel, that this pixel, the red pixel in the quad, only had red values. So we have to give it that information. And then past that, we don't have to do anything about any mosaicing, demosaicing, any sort of Bayer stuff. It's just all totally abstracted away via this 3D reconstruction thing. I'm sure many people in this audience have tried to write a demosaicing algorithm. We don't have to do that. The 3D model just demosaics for you. And there's nothing about that model that is specific to the Bayer quad, right? So if someone came to us with a whole new kind of camera where there were weird clear pixels or some irregular pattern, even if it wasn't even a grid, it would be fine, right? We would just cast rays through whatever pixel and just note what color it comes with. So you can, I think there's room for some really cool stuff here where you could imagine co-designing your camera sensor with this idea of 3D reconstruction. But this is not really my expertise, but it seems like there's a lot of potential here. And you could never have to write a demosaicing algorithm ever again. So that's kind of the really relevant camera stuff that I have. And then I thought I would take a departure into kind of more generative AI stuff, because I feel like it's going to be fun to have a Q&A where you all have an excuse to ask me weird questions about AI stuff. So this is a project that we had. This was published at iClear this past year, where it won an award. And this was basically the first paper to do kind of generative 3D, so text to 3D. And this is built on the back of NeRF, of a neural radiance field. But it also, of course, relies on a lot of the generative AI stuff that has been happening the last couple of years. So text to 2D. This is a thing you've all seen by now. Well, not this image in particular, but hopefully everyone is aware that text to 2D, 2D image synthesis is now a big thing. And yeah, we're great at this. This went from a totally unsolved problem to basically a solved problem over the course of 2 years, which is insane to me. So these are results from Imagine. This was Google's in-house 2D image synthesis system that came out about, I guess, 2 years ago now. And this is the result for a DSLR photo of a peacock on a surfboard. And you can see that those do look like peacocks on surfboards. This is a very believable result. And this result is, at this point, 2 years old. If you use DALL-E 3 today from OpenAI, you'll get results that are significantly higher quality and very striking. So this works really well. Text to 3D, when we wrote this paper, hadn't happened yet. Although some people were trying. There was some work on this. And there was enough work that there was kind of a paradigm that kind of emerged as to how you would solve these problems. So you'd collect a big 3D data set. In practice, here big is in scare quotes because it's actually very hard to get 100,000 or a million 3D models. They're kind of expensive and artists needs to make them. And you can collect a medium-sized data set and you can train basically the 3D version of one of these 2D image diffusion models, and you get results that look kind of like this. These are results from OpenAI's Shapey model, which came out not too long ago. And yeah, there's a big quality gap here between that penguin and the peacock that I showed in the last page. Like this is a much harder problem, in part because there just isn't that much 3D data to train on. So thinking about this problem, we realized that, so one big takeaway from everything you've seen about LLMs and image diffusion is that scale is critical, right? Like scale maximalism is just correct in an AI context. You need lots and lots of trained data to make these systems really magical. And this is a problem for 3D because we just don't have very many 3D worlds, 3D models. 3D models represent a vanishingly small fraction of the visual world. And images represent, a small subset of the visual world, but like a pretty enormous, like a pile of data, right? Everyone in their pocket has a piece of glass that they can use to take photorealistic renderings of the thing they're looking at. Photos are photoreal, they are perfect, and we have trillions of them, and getting text annotations for them is not that hard. So because of that, we thought, we shouldn't try to do 3D generation by using 3D data. We should try to use 2D models to do 3D data because we already have these very powerful 2D models and they have all the scale in terms of data that we need. So going back to NeRF, so you can just take this NeRF model, this exact same rendering engine and everything, and you can say, okay, forget the loss function. I don't want my renderings to look like an image that I'm going to give the model. Instead, I just want those renderings to look like they correspond to a text prompt. So everyone always thinks that the thing we're doing is we're using text to 2D to make a bunch of images and we're feeding them to NeRF. We're not doing that. That actually works very poorly. Instead, what we're doing is we're going to recover a NeRF where every time we render it from different points of view, we just ask someone else's diffusion model, hey, does this look like a peacock on a surfboard? And that diffusion model will say yes or no and nudge us in the right direction. So all we're doing is swapping this loss function out for a loss function that came from a diffusion model, from a generative process. Image diffusion is a really fascinating subject. I recommend learning about it. Here are some papers that you could search. I'm not going to be the person to teach you this in the remaining 17 minutes, in part because I don't have the expertise, but also I don't have the time. This is a very rich subject, and I just at a very high level, the way these models work is there is an analytical process that corrupts an image. So you just add Gaussian noise to an image to make it bad, and these models learn to undo that process and make noise into an image. And then when you're done training one of these models, you can take an image of all noise and a text prompt and just iteratively update that noise pattern until it becomes an image that resembles the text prompt. That's at a very high level how these models work. So here's kind of the overall pipeline that we're going to have. We're going to have a NeRF, and this is slightly different from a normal NeRF. This is actually a density field and an albedo field, so the color is not radiance, but it's paint. It's what color is this paint, because we want to disentangle lighting effects, and we want like an actual 3D model that we could relight. We take that, we linearize it into the surface normals, we have a randomly generated light source that we take a dot product with, and you get a shading image. You multiply that into the albedo, and you get an image that you can render from a certain point of view. I'm just describing Lambertian reflectance. This is not sophisticated. You get this rendering that you can then corrupt and then feed to a denoising model. This, again, is someone else's denoising model. Some hardworking people at Google worked really hard to train a very, very good 2D diffusion model that we are just going to take off the shelf, not touch, not change in any way, and just, its weights are all frozen. And what that lets us do is we can feed it an image that we've kind of corrupted with some noise, and we get a signal out that says, oh, this image would look more like a peacock if that thing was a little more green and that thing was a little more blue, something like that. And then we backpropagate that through the entire rendering model, and we get new weights. So the way you should think of this is, at the beginning of the process, we initialize a 3D world that is just noise, it's garbage. And then some painter-sculptor type, some AI painter-sculptor, looks at it from a certain angle and says, that's not right. This should be a different color. That should be a little further away. And then nudges it, and then looks at it from a different angle, sees what's wrong, nudges it a little bit again. And that's what this is. That's what this process is. So We start off initialized to nothing. This is going to loop a few times. And that peacock just kind of comes into focus. And yeah, it's kind of magical that this works at all. Then when you're done, you have a 3D model that is, again, this is just a 3D model, right? All we've done is parameterize a 3D model in a kind of confusing way. But it's a real 3D model. You can look at it from different angles, and it's rock solid. It doesn't look strange as you zoom around it because we're just rendering a 3D model. It's kind of amazing this works at all, right? Because the model that this was trained with has never seen 3D before, right? It's just a 2D diffusion model that was trained on many, many JPEGs taken from the internet, and a 3D rendering engine that allows gradients to flow through it, which is NeRF. And then you put those together, you get this ability to hallucinate 3D objects out of nothing, or out of text prompts. Here's a fun wall of results. These results, at this point, are like 18 months old, so the state of the art in the literature is actually a lot nicer looking than this, but I think these results are pretty fun to look at, in part because we just kind of went crazy coming up with really elaborate prompts describing strange combinations of things, which is obviously fun, but also an important stress test for these models, because some papers will show generative 3D results where they train on some dogs, they train on some cats, and they show you a dog-cat hybrid or something, and it kind of works. And that's not that hard. Like interpolating between data points in your training set is, that's a thing that you can do with a much less sophisticated model, but it's very hard to get this sort of compositionality where you can say, a robot looking at his laptop while lying on a couch, and actually have that happen. That requires like a really deep understanding of these models, which is what we can get by using state-of-the-art 2D diffusion models that have lots and lots of data. So if anyone ever shows you generative 3D results, always look for the weird stuff. If someone's not showing you crazy combinations of things, it's probably because the model can't actually make those. So we have some fun demos on the website where you can kind of simulate being an artist making assets out of this pipeline by customizing a text prompt. In practice, this was done by just rendering out the Cartesian product of all possible texts and just pre-rendering them and letting you flip between them, but it's pretty fun. And these are 3D models. You can do all the things you would want to do with 3D models with them. The website has like an AR demo that's kind of cool. And we put this online, and within a day, people were putting these models, this hamburger ghost, into video games, and it works just fine. It's just a 3D model, or printing them out. And people have even started just making whole video games with this technology. So you sit down, you type out a bunch of text prompts of things you want, you make 3D models, and then boom, you have assets for some sort of video game or VR experience or what have you. And people have also kind of leveraged this technology, this is not our work, into monocular 3D tasks. So here you're not conditioned on a text prompt, you're conditioned on an input image, and the model is trying to recover what's basically a NeRF of the whole 3D scene. And I can't believe how well this works. This really surprised me when it came online, but this is very clearly working pretty well. We have some recent work in the subject. So I find this whole generative AI thing to be obviously compelling and interesting. But the text to 3D use case didn't really interest me that much as the kind of classic 3D reconstruction problem interests me. And NeRF has a lot of problems in like the classic regime, where if you give a NeRF 3 images of a scene instead of 300, it will fall apart pretty badly. And that's just because the problem is very under-constrained and there's a lot of degenerate solutions. And this is the sort of result we would get from state-of-the-art NeRF models if you just didn't give it enough data. But one really cool thing that these generative AI techniques give you is you could build a diffusion model trained on lots of data that is a multi-image diffusion model. So you've conditioned on multiple input images, and then the model has beliefs about what unseen views that might have. What the unseen views should look like. And you can plug that into a NeRF pipeline and then suddenly get these wonderful 3D reconstructions from as few as 3 images. So this is expensive. You're evaluating a diffusion model all the time. It's not quite ready for prime time, but I think this is a really nice step towards making these models more generally applicable in terms of like data set consumption and stuff like that. And that's it for me. Thanks, everyone.